We are on the ground floor of the Pete V. Domenici Science Operations Building, and with us is Keith Morris, the LOIF engineer. We're in front of the EVLA's Test Rack, and Keith, can you explain to us what all this is for? What's it about?
Well, sure. When the Very Large Array was first constructed, we didn't have this building. All of the technical staff was at the VLA site. If a problem arose in the fields, if they wanted to test out a new module, they were there. They could simply test it out on the antenna. By the time the EVLA project came along, we had this facility here with most of the design engineers and production technicians stationed here. Mm-hmm. We needed a way to one, prove out the modules before we installed them, and two, repair modules that failed in the field. So to do that, we built what's more or less a complete system, a complete electronic system, such as we would have at the central building and the antenna here in the basement. There are two racks of electronic modules here. This is a replica of the central building electronics, the master frequency references, clock signals, and so forth that are sent to all the antennas. This is an example of the antenna electronics. The central buildings are connected to the antennas by up to 13 miles of fiber. So we've installed 13 miles of fiber in a rack in the corner here.
So in effect, this represents the entire length of one of the arms of the EVLA then?
That's right. Okay.
On another part of our tour, we actually had visited Antenna 24 and opened up its rack, which is the same kind of rack as this, but we didn't notice this, what I might call, admiringly perhaps, a rat's nest of cables and fibers and things. So what's the difference between that rack and this rack?
Well, the difference, that's a permanent installation. This is a dynamic, constantly evolving situation. As modules fail in the field, they need to come back here. We never know which module is going to fail, so I have to maintain the flexibility to plug in a module where it needs to go. And for that reason, maintaining neat wiring is almost impossible.
And I guess, although it may not seem obvious, that although there's only 50 miles between here and the VLA site, it's just not practical to shuttle the module from here down to there. You need this in situ facility to actually effectively work. This is right?
We do. Our test equipment is here. A round trip to the VLA takes maybe almost 3 hours out of the workday. Yeah. So it would be inefficient for one. Right. Inefficient to maintain two sets of test equipment. We need them here, and so forth. So
yeah, and I could imagine. Sorry, there, Keith. I could imagine that a module might be completed down here, thought to be working in some local facility. You go up to the site, you plug it in. There's something wrong, and the guys you need are not there.
They're not there, and the equipment you need is not there. Right. So hauling these machines up the antenna is impractical. Another thing we have the ability to do is to suppose we thought of an improvement for a design. Mm-hmm. We could have a new module and an old module, new design and old design in parallel, do A/B comparisons between the two in real time.
Sure.
Prove out the performance of new designs.
So Keith, we're looking at the back side of this rack, the business end, but let's go to the front side because that presents a rather different appearance.
It does.
So we're now on the front side of the same pair of test racks, and it's a very different appearance. This is the same side that we showed when we visited Antenna 24. And where are the cables? Where are the plug-ins? Where are the readouts? Why are we looking at such a blank front?
That's right. Well, it's all in the rear of the modules. This is for help in identifying them. In fact, the first antenna that we built with this side facing into the room in the antenna. Yeah. Because this was the nice, pretty side.
Yeah.
The first time something went wrong in one of those modules, we realized why that was a problem. That we had to squeeze into the 18-inch space behind the rack in order to disconnect cables. So all subsequent antennas were built with this side facing towards the wall and the cable side facing into the room for access.
Keith, I noticed there's another pair of modules down here. They're very different. I see they've got rather old-fashioned looking readouts and buttons and lights and switches. What are we looking at here?
So these are a pair of original VLA modules. These are the receiver control modules. They have knobs, they have LEDs, which were used for monitoring and controlling the receivers from the front panel. With EVLA, we made a calculated decision not to have such features on the fronts of the modules. Mm-hmm. One, we have remote computerized interfaces to do that, so we don't really require an operator standing at the front of the module to do it. Right. Two, they present an opportunity for radio frequency interference to leak in or out of the module.
Right.
So the EVLA modules were all a sealed, shielded design. The only penetrations in the module are shielded against radio frequency interference, and the inner workings of them are available from a computer interface.
Right, so that when technicians, engineers, some cases scientists, certainly the operators need to know what's going on inside any one of these modules, they don't need to journey out to the antenna to plug in the test equipment, right?
That's right. Yeah, it can be done even from this building. We can diagnose problems on the antenna from our desk here.
And I suppose if you knew the proper protocols, you could be on the other side of the earth and still do it. Is that right?
That's right. Yep. In fact, we often do. Yeah. So.